All right, hey, I know that we spent a lot of Monday's class going over the midterm, and so you only had about a quarter of the usual time to work on homework. Um, Nonetheless, people made good progress on the homework, and in some cases, it looks like you're on the right track. In some cases, there's some common errors that I'm seeing. So I wanted to go through at least some of the questions on the homework. And if you're still working on the homework, don't watch this video unless you're stuck. Um, Try it yourself first, and then come back here and see how you did. But if you're stuck, or if you already did the homework as far as you think you can, and you want to know how you did, in addition to the feedback I'm putting on your actual homework, here's a quick run through on the basic way that we do most of these questions related to timers. So the first question wants to know the values for the high and low timer registers and the prescaler that we need to set up the timer to trigger after 1 second. Okay, so everything that we do is based, unless we say otherwise, on this idea of a 32 kilohertz system clock. And remember, we don't usually deal with that. That's just sort of the underlying clock rate. It's actually 31K, but we round it up to 32. But we divide that by 4, and we get an 8,000 kilohertz, 8,000 hertz, um, or 8 kilohertz instruction clock. So what does this mean? 8,000 instructions per second. That's kind of the golden metric that we've been working with all of the timing related stuff. So how does this relate when we actually use a timing subsystem? So timer 1, it's a 16-bit timer, and we want it to fire after 1 second. So 1 second is 8,000 instruction cycles. Okay, next thing to remember, these timers, they count up. They start at whatever value you load into the timer registers, and they increment. And by default, they increment each instruction cycle. And they overflow when they run out of bits. So a 16-bit counter will overflow at 65,536. It's 2 to the 16th, right? So one more than the largest value, which is 65,535. So this is where the timer will fire an interrupt request. And so if we want this to be the count value after 8,000 instruction cycles, subtract 8,000. And so 57,536, that should be the initial value in the timer registers. And this is for a 1-to-1 prescaler. So what values do we put into our timer registers? Well, take 57,536, convert it to hex, and you get E0, C0. So E0, this goes into the high register, this goes into the low register. So our initialization condition is timer 0, H equals E0, timer 0, L equals C0. Remember, these are 8-bit registers, but we're trying to represent a 16-bit number. So what do? We take our 16 bits, we break it in half. Put the 8 most significant bits into the high, put the 8 least significant bits into the low. And then if we want to set up the T1 configuration register, T1 con, so I touched on this towards the end of class. So let's just go through this again. Let's go ahead and set this RD16 bit to be a 1, because what we want is we want the read and write to happen as if it were a 16-bit operation. This is the business of loading one register first and then loading the other, and when you load that second one, it pops both of them into the actual timer register. So we're going to set this up for 16-bit operation. The system clock, we're not going to monkey with that. We can set the system clock to come from a different oscillator. We're just going to leave bit 6 as a 0. And then bits 5 and 4, these will be the prescaler value. And for us, we want a 1-to-1 prescaler. This says set these to 0, 0. But these two bits will change depending on what what prescaler we want. So leave that at 0, 0. And then bit 3, do we want the timer 1 oscillator on or off? We can leave that off. So that's useful if we're going to use the oscillator to drive the system clock. And then bit 2 is when we have an external clock input. We're not going to use an external clock for the timer, so we'll leave this at a 0. Bit 1 says, where does the timer 1 clock come from? We want it to come from the internal clock. And this f-osc, that's the frequency of the main oscillator, that's the system clock, 32 kilohertz. We divide by 4, the internal clock is 8 kilohertz, so we want to leave this bit as a 0. And then to turn the timer on, we make this least significant bit a 1. So that says turn on. This says 16-bit reading and writing. And then these 2 bits here are the prescaler, anywhere from 1 to 1 up to 1 to 8. So that would be the T1 con value, but all I was asking for in the question here was actually what's the prescaler, and so you can just say it's 1 to 1. Okay, so we can modify this behavior, this process pretty simply to do these other questions. So the next question is we want 5 seconds. Well, it's 8,000 instruction cycles per second, so if we do 8,000 times 5, that's 40,000 instruction cycles. And we're going to overflow at 65,536, subtract 40,000, that's 25,536. So put that into hex, and it's 63 C0. So 63 goes into the high byte, C0 goes into the low byte, and our prescaler is still 1 to 1, so T1 con is the same as it was. Okay, the next question, we want 10 seconds. So 8,000 times 10 equals 80,000 instruction cycles. If we try to do the same thing, 65,536 minus 80,000, we get a negative number. We would have to start our timer registers at something smaller than 0 so that it takes 80,000 ticks to overflow. That's not possible. So what do? We use a prescaler. So we can set a 1 to 2 prescaler. And so 80,000 instruction cycles, if we set a 1 to 2, this will be 40,000 increments. Remember how the prescaler works, the monkey that's catching the drops of water and only letting every other one through. So every other instruction cycle increments the timer register. So if we have 80,000 instruction cycles with a 1 to 2 prescaler, we only increment our register 40,000 times. So we actually want to initialize to 40,000 less than our overflow, which is 25,536, which is the same example we had up there. So again, timer 0H will be hex 63. Timer 0L will be hex C0. So we put in the same initial timer values, but we use a 1 to 2 prescaler, and that 1 to 2 prescaler would make our T1 configuration 1001, 0001. So hex 91. Alright, questions 4 and 5 ask for 10 seconds with a different prescaler. So this is now a pattern. If we were to use a 1 to 4 prescaler, we know that 10 seconds we still want 80,000 instruction cycles, but if we have a 1 to 4 prescaler, that's 20,000 increments, and so we initialize to 65,536 minus 20,000 equals 45,536. If we want a different prescaler, 80,000 instruction cycles with a 1 to 8 prescaler means we'll end up with 10,000 increments. And so 65,536 minus 10,000 is 55,536. So convert these to hex, that's the value you put into timer 0 high and low. All right, and then the discussion question. Since we have multiple options, we can use different prescalers. Which one should we pick? And the best prescaler is going to be the smallest one. The reason being, in this case it didn't make any difference, but if we use a prescaler of 1 to 8, then every 8 instruction cycles causes an increment. The reason we're using prescalers is because the value that we want to actually load into the timer registers isn't an option, right? We want to increment after 80,000 increments. We want to overflow, but we can't set the timer register so that it overflows after 80,000. So we're breaking down. We're effectively increasing how long the instruction cycle lasts, right? We're basically saying the instruction cycle takes 2/8,000ths of a second instead of 1, right? So the larger the prescaler, the coarser that chunk of time is, and the harder it's going to be to get exactly the timing interval that we want. In other words, if we wanted to wait exactly 7 instruction cycles, and we use a 1-to-1 prescaler, we could just initialize to this value, and that would be exact. If we use a 1-to-2 prescaler, we would want to wait 3.5 instruction cycles. Well, we can't do that, right? We can't initialize this to this number minus 3.5. We'd have to either do this minus 3 or this minus 4. And so there's a rounding that takes place. So the smaller prescaler gets us a more accurate value. All right, and then what's the shortest time interval possible with timer 1? So I mean, we could do a time interval of 0, but that's an edge case. The smallest we can practically get is overflow after 1 instruction cycle. So we could initialize our timer register to 65,535, use a 1-to-1 prescaler, and after a single instruction cycle, our timer will overflow. So that's 1/8000th of a second, which is 125 microseconds. So that's the shortest interval. The largest interval is going to come when we make the prescaler as large as possible, so that's 1 to 8, and we initialize timer 0 to 0. So that's going to take 65,536 times 8 instruction cycles. So it's this many. And if we divide by 8,000 instruction cycles per second, we're going to get about 65 seconds. So we can get this timer to wait anywhere from 1/8 of a millisecond to a little over a minute. All right, and then on the timer 2 questions, timer 2 works differently because it counts up. It starts at 0 and it counts until it reaches the value of PR2. So if we want an interrupt every 1,000th of a second, what do we have to do? Well, so timer 2, it's an 8-bit timer, so we can only count up to 255 and request an overflow then. So if we want an interrupt after 1,000th of a second, that's 8 instruction cycles. So we can set PR2 to 8. We'd actually set it to 7. There's a factor of plus or minus 1, but we'll just say we'll set PR2 to 8, and that means that after 8 instruction cycles, assuming we use a 1-to-1 prescaler, after 8 instruction cycles, the timer 2 register will equal 8. It'll request an interrupt, and it'll reset that register to 0. And so the way we load the configuration register would be something like T2con. Well, bit 7 doesn't matter, so we can just make that as 0. Bits 6 through 3 are the post scaler, and we're just doing a 1-to-1, so we'll make those all 0. And then bits 1 and 0 are the prescaler, and that's also going to be 0, 0. And oh, and timer 2 has to be turned on, so we have to put a 1 right here. So this turns it on. That's the pre-scaler. This is the post-scaler. The effect of the pre-scaler, post-scaler, remember, is we just multiply them. So if this is 1 to 2 and this is 1 to 4, the effect is a 1 to 8 pre-scaler. All right, so for a 1/1000th of a second, we could set T2 con equal to hex 4, which just turns it on, has no pre-scaler, post-scaler, and we could set PR2 equal to 8. And so it's the same process for these other questions. So suppose we want to wait for 1 second. So 1 second is 8,000 instruction cycles. Well, we can't set PR2 to 8,000 because it's only an 8-bit register. It can only go up to 256. So how big a pre-scaler do we need? Well, let's do 8,000 divided by 256. We're going to need at least a 31 pre-scaler. So let's set a pre-scaler of 32. So we could do a 16 to 1 pre-scaler and a 1 to 2 post-scaler. So let's say post-scaler equals 1 to 2, pre-scaler equals 1 to 16. So that's effectively 32, and now if we do 8,000 divided by 32, that's 250. So we want to overflow after 250 increments. And remember, every 32 instruction cycles will make 1 increment. So 250 increments will correspond to 250 times 32, 8,000 instruction cycles. So we set the PR2 register to be 250 decimal. And then we would set T2 con. In this case, we want the post-scaler to be 1 to 2. So that's going to be post-scaler of 1 to 2 says it should be 0, 0, 0, 1. And then we have our on bit, and then our pre-scaler should be 16. So that can be a 1 followed by anything. So we can just make it a 1. And so there's our T2 con value, and that's 0F. So that's how all of these problems work, right? With timers 0, 1, and 3, figure out how many instruction cycles you want. That's how you translate the required time into instruction cycles. And then if you can cause an overflow after that many increments, just load that value in, subtracted from the overflow point, 65,536 or 256. But if you need more increments than you can put in to your initial value, use the pre-scaler. So if we want to count up, 100,000 instruction cycles, well, if we do a 1 to 2 pre-scaler, 100,000 instruction cycles would correspond to 50,000 increments. And if we have a 16-bit register, then we just initialize it to 65,536 minus 50,000. Timer 2, same initial setup, but when we determine how many increments we want, that's the value we load into PR2 instead of loading, 65K minus that or 256 minus that. So shortest interval possible, again, is just a single increment. We could set PR2 to 1, 1 to 1 pre-scaler, post-scaler, and that's an 8,000th of a second, 125 microsecond. Longest time interval possible, well, what's the biggest pre-scaler we can get? We can do a 1 to 16, and the 1 to 16, that's going to be a pre-scaler of 256. And we can set PR2 to 255, so it will take 256 increments to overflow. So that's 65,000 instruction cycles. Divided by 8,000, it's a little over 8 seconds. That's the longest we can cause timer 2 to delay before requesting an interrupt. All right, so that's the basic idea. Think about those. If you were unsure about the homework, go back and look at those questions. Look at what you did or what you're doing, and bring questions to class tomorrow. All right, thanks. Bye.